We're going to talk about the aeroelastic effect. So aeroelasticity is, we'll see, is an interaction between the airflow and the stiffness of the structure. And at the end, I'll do the class evaluation forms, or near the end, maybe in one of the last breaks. And I need a couple of volunteers to collect them and take them back to the office, because after I hand them out, I'm not allowed to touch them. So we'll get cracking. Aeroelasticity is a mutual interaction between the inertial, elastic, and aerodynamic forces acting on an aircraft structure. So the airstream that the plane is moving through has energy in it. Well, the plane has kinetic energy, but if we change our reference frame, the airstream has kinetic energy. And it can excite oscillation, or it can excite deflections in the airframe. And those deflections can be quite catastrophic, as we'll see in a little while. Now, I'm going to refer to a few things that might test the memory banks. I'll refer to a bit of vibration, which you did last year. And I'll also refer to a few aerodynamic concepts that you haven't learnt yet, but I'll give you a quick introduction to them. But inertia forces on the airframe are forces resisting acceleration. So if we think about Newton's second law, F equals ma, we can think about the ma part as really a force of sorts. If we take it to the other side of the equation, we can make it mx double dot on the left-hand side of the equation, and it's effectively a force. Elastic forces are our typical kind of spring forces that we're all used to. Things that are proportional to deflection, so kx kind of forces. And aerodynamic forces, as we'll see, are pressures and skin frictions acting on lifting surfaces, or non-lifting surfaces. But all of these problems are relating to surfaces that generate lift. So we have a few types of problem here. We have aeroelasticity in general can be broken down into a few types. Okay, we have static problems, dynamic problems, and the kind of distribution the kinds of problems within those categories. For static, which we'll cover first, we have load redistribution, divergence, and control reversal. These are all issues that we need to deal with. And for the dynamic problems, we will only really consider flutter, but flutter, buffeting, and dynamic response. And just as an aside, when we're talking about aeroelasticity, we need to talk about equilibrium and where equilibrium is maintained. We have three types of equilibrium that we can consider. Stable equilibrium, or equilibria, are where we have, for instance, a ball in a cup like this. If we disturb the ball, there's a restoring force that brings it back to the center. And if it's got some kinetic energy, when it gets to the center, it will overshoot and you'll get a little oscillation. An unstable equilibrium, if it's completely undisturbed, it'll stay there, but any little disturbance will cause it to fall away and it'll never return to the mean position. And a neutral equilibrium, if we disturb it, it just stays where it was disturbed to. Okay, so the first aeroelastic issue is load redistribution. Now, I'll have to introduce a few concepts here. I'm not sure how deep into the aerodynamics you've gone. I know you've done a little bit of flight mechanics, but when we look at an airfoil, we can define a point called an aerodynamic center. Have you been introduced to an aerodynamic center yet? Yes? No? Does anyone know the definition of an aerodynamic center?
There's no change in pitching
Yes, exactly right. So it's a point on there's two aerodynamic centers that we can think of. Center of pressure is the point where we can assume that all the lift acts through if we didn't want any pitching moment. Then there's an aerodynamic center, which is a slightly more useful point from structural analysis perspective. It's the point at which the pitching moment doesn't change when we change angle of attack. So if we had an airfoil like this and we changed the angle of attack, then the lift can change because lift is proportional in some way to angle of attack, but the moment won't change, and that just makes some of our analyses a little bit easier. Now, this is the 2D kind of problem that we'll look at quite a few times. Generally, the elastic axis, or the center of twist for a wing, it's exaggerated here, but generally it's behind the aerodynamic center. So when lift is generated, it causes an upward pitch about that center of twist. So wings are big torsional springs. If we apply a moment or a torque to them, they will twist about a particular center, and in a 2D case that can be thought of as the shear center, but it's not really the shear center for a general 3D case. But there's some point about which the wing will twist, and we call that the elastic axis. Now, if we put a lift on here, that creates a twist, but that twist increases the angle of attack, which creates more lift. So that extra lift creates more twist. So we end up with a situation where the twist generated actually increases beyond where it should from a static case, because as the angle of attack goes up, it's generating more and more lift. So the only thing that stops it twisting right around and the wing kind of twisting clean off the aircraft is the stiffness of the wing. So the wing stiffness, which is this spring here, eventually stops that twist. And we think of the angle in two parts. We have the angle of attack to the airflow, and then we have a theta here, which we use quite a bit in our calculations, which is the twisting angle. So there's the angle of attack that the airfoil starts with, and then there's the amount that it twists relative to the root of the wing. Now, if the aircraft's not flying too fast, eventually the spring stiffness or the torsional stiffness of the wing overcomes that twisting action, or they form a stable equilibrium, and the lift distribution changes. So what happens is, because the spring stiffness of the wing, or the torsional stiffness, is getting lower as we go out. Imagine that you tried to twist the wing right down near the root. It wouldn't twist very much. But if you stood right out near the tip and tried to twist it, it'd be more compliant. The spring stiffness would be lower. So the further out you go, the lower the spring stiffness, so the more the twist. So what the effect of the aeroelastic effect on the lift distribution is that near the tips, there's higher lift generated than near the root. Now, we know what Schrenk distribution looks like, and I've put on top of that a red dotted curve here, which is an exaggerated change due to aeroelastic effects. Now, why would that be a problem if we're getting more lift generated near our wing tips than near our wing root? Yeah, it increases the bending moment on the wing. So if we've got more lift out here, the total lift is the same. If we've got more of it near the wingtip and less of it near the wing root, the bending moment at the wing root is bigger. So it puts more stress on our structure, it increases our fatigue loads, and it decreases the lifespan of the aircraft. So this is not a good thing, and in some cases they'll even wash out, what they call wash out the tips of the wings. The wings will actually have a slightly lower angle of attack at the tip than they will at the root, so that this effect is negated. So there's a slight, when they put the wing on the aircraft, they'll have a slight twist in it to start with, so that when it does fly and experience lift, it twists back to the right angle of attack. So they will wash out the tips very slightly. Okay, so I'm about to have to do a calculation here, and I don't have my Megson notes with me, so I'll need a second here to dig them up on the computer. So we know that aerodynamic loads are proportional to the square of the velocity of the aircraft. So we said we had an equilibrium formed here between the twist of the wing, or the aerodynamic loads, and the stiffness of the wing that balances that twist. But eventually, because the lift is proportional to the square of the velocity of the aircraft is not getting stronger as it flies faster or stiffer as it flies faster. The stiffness of the wing is fixed, whereas the lift is really not fixed. It's proportional to the velocity. There is eventually a speed at which the wings will literally twist off the aircraft, and it's called the divergence speed, and it limits the maximum speed that our aircraft can fly. Most of our upper limits on our design regulations are derived in some way from the divergence speed of the wings. And so when you see something like a design dive speed, that design dive speed is in some way related to the divergence speed at which the wings will twist off the aircraft. It's nothing to do with how fast the engines can push the aircraft or any of these things that people might think. It's literally how much structure can resist the aerodynamic forces before it twists itself into oblivion. Okay, so we'll do a calculation on that, and I'll just give me a minute to dig out my notes. Okay, so first things first, let's set up this problem. What we want is a sum of moments about the center of twist here. And we'll say clockwise is positive. So this C here is the chord of the wing, and E is a constant which doesn't really have a name, but it's a proportion of the chord of the wing. So we can think of it as a fraction. So E might be 0.1, 0.2, but it's some fraction, it's something less than 1. So the moment of the lift of about the center of twist is LEC. The moment from this M0 is M0. We have a restoring moment from our torsional spring of minus k theta. So what we're trying to work out is, if we're thinking of divergent speed, we're trying to find the speed at which the angle of twist gets very large. So we can't work out exactly when that will be, but we can work out a velocity at which the angle of twist quickly approaches infinity. So what we've got to do is get an equation where this theta, this angle of twist, is the subject. Now, what terms in here are related to angle of twist? Well, we know, because we've picked our moments about the aerodynamic center, that this is not a function of theta. There's no theta hidden in there. The angle of attack or the angle of twist doesn't affect our moment at all. But this lift does have a hidden angle of twist in it, because our lift is in some way related to the angle of attack of the wing relative to the airflow. So if our twist is changing, the angle of the airfoil to the airflow is also changing. Okay, so we have new expressions here for lift and moment. Lift, half rho v squared SCL. Moment is half rho v squared SC to give us a moment, times the coefficient of moment about the aerodynamic center. Now, we still haven't exposed any theta yet. So where does our theta come in? Well, our CL, what does CL look like relative to the angle of attack? Okay, I'm going to write on this axis alpha plus theta, because this is the total angle of attack of the wing relative to the airflow. And on this axis, I'm going to draw CL. Does anyone know what this curve looks like? Have you been introduced to this yet? Okay. Yeah, so there's a line of approximately 2 pi. Does it start at the origin or does it start at offset? Yeah, so in general for an airfoil, it does something like that. There's some offset, which we'll call, for our argument's sake, CL naught. And then for this calculation, we're going to say that has a slope dCl d alpha. So the CL at any point, we can find from CL naught plus dCl d alpha, alpha plus theta. Okay, and this can be approximated by 2 pi. Okay, it's not exactly 2 pi, but it's a pretty good approximation. So let's substitute that in. Okay, is there any more hiding thetas anywhere? Oh, sorry, I'm missing the perpendicular.
No, the theta's hiding to DEC.
Okay, we're going to assume that it's small angles, relatively small angles, because a small angle of a twist is enough to break the wing. So we're going to assume that EC doesn't change with theta, or it changes a very small amount. Because by the time the wing's twisted around enough that EC is changing, you've got bigger problems than worrying about an extra sine theta or cos theta. All right, so let me just have a look here. What we have to do now is substitute these back into the main moment equation, and we've got to rearrange so that theta is the subject, because what we're trying to find is if there's an unstable speed at which theta gets very large. And I can tell you now that that is going to be the case. So let's do our rearrangement. So we've got half rho v squared s CL naught plus dCl d alpha, alpha plus theta. I can get rid of that. Times this length EC plus half rho v squared SC Cm naught minus k theta equals 0. So what we're going to do is get all the terms with theta on one side of the equation and all the terms without theta on the other side of the equation. So there's a half rho v squared s here, and there's a half rho v squared s here. I can send my theta over the other side. So let's do a little bit of fiddling here. Half rho v squared s. Now, remaining on this side of the equation, we're going to have CL naught plus dCl d alpha times alpha. times that whole bit there times EC. And we're going to have a plus C Cm naught. I think just make sure I'm doing the right thing. You guys can do algebra as well. And I can almost guarantee I'll make a mistake somewhere. On the other side of the equation, we're going to get k theta minus, what we need to do is take this theta over to the right-hand side. So we're going to have minus half rho v squared s dCl d alpha times theta times EC. You still with me? I haven't made any mistakes yet, I hope. So again, if we rearrange to make theta the subject, we end up with the numerator of half rho v squared s Cl naught plus dCl d alpha with an EC in here plus C Cm naught, and on the denominator we end up with K minus half rho v squared s dCl d alpha EC. So this is a 2D case. It's a little bit of a sort of approximation. We can't really do this calculation for a real wing because a real wing doesn't have a constant K because it's finite. The K is different at every station. This is a 2D approximation assuming we had something like an airfoil in a wind tunnel and we had a torsional spring resisting that the motion of the airfoil. We could do this because we could measure the torsional stiffness K of our spring and we could work out exactly what the divergent speed is. For a finite wing, we need to do a slightly more complicated calculation, which we'll see in a minute. But it does open our eyes to a lot of things. When is this theta going to get very big? So what does this term, what does the V start at when you start flying? 0 and you build up speed. And so this term starts small and starts getting bigger because everything else in here is fairly independent of the flight condition. S is fixed by the aircraft, E and C are fixed by the aircraft, dCl d alpha is fixed by the airfoil selection, or it's pretty constant anyway. So this term starts small and starts building up. Eventually this term is going to equal our K. And so at that point, theta gets very big very quickly. So in the limit, we can say that theta tends to infinity when K equals half rho v squared s dCl d alpha dc, or V equals the square root of 2k on rho v squared, sorry, there's no V anymore, rho s dCl d alpha EC. Okay, and we call this divergence speed. So remember that we want to increase the divergence speed. We want to have the biggest possible flight window. we don't want to be limited in the maximum speed that the aircraft can fly, or at least we need to know where it is. So our goal when we're designing aircraft is to get this as big as possible. So how do we get that bigger? What terms can we change here? Yeah, so we can increase the torsional stiffness of our wing. So it's a little bit iffy what that means at this stage, but realistically it's increasing the G or the J for our wing. So it's increasing the amount of material that's away from the torsional axis. So increasing our skin thickness, moving material towards the outside of our wing section, which is what we do anyway, but increasing the depth of the wing has a big effect because it increases the enclosed area inside our wing box. On the flip side, the only thing we can really manipulate on the bottom of this equation is the distance between the aerodynamic center and our elastic axis. So what we generally try and do is move our elastic axis as far forward as we possibly can, and we do that by putting a little bit more material forward in the wing rather than back in the wing. So moving our elastic axis is another potential way of adjusting our divergence speed. But this one's a bit harder to control than the K is. Okay, so the next complication is what happens when we move to swept wings. And why is it, do you think, that high-speed aircraft have swept wings generally? Well, the primary reason that aircraft that travel near the speed of sound have swept wings is because of divergence. When you sweep the wing back, the elastic axis I'm going to have to get my pen working here. The elastic axis of the wing means that the lift that's generated outboard, when the wing bends, it actually twists the wing forward. So it counteracts the twist that we would get in the normal condition. So it's a self-limiting problem. So when we sweep our wings, when you generate lift, you generate bending. That bending actually twists the wing forward and cancels out any divergence effect. So we can increase our divergence speed very dramatically by sweeping our wings backwards. On the flip side, has anyone seen an aircraft with forward swept wings? There are a few. You get some significant performance benefits for manoeuvrability with forward swept wings. So there are some vehicles that have forward swept wings, but not many. And the reason is that the divergence speed, you need much, much stiffer wings to get the aircraft at a flyable speed. You cut your maximum velocity quite dramatically if you have forward swept wings, unless you can make them very, very stiff. So you need to have generally composite wings, and they need to be very, very thick composite wings. But if your aircraft is performance dominated, then there are some cases where going to a forward swept wing might be useful. We're going to consider another aeroelastic problem known as control reversal. So when a pilot wants to roll the aircraft to the left, which way do the ailerons deflect? The right, what on the pilot's right wing, which way does the aileron go? Down. Yeah, because it's trying to generate more lift. Okay, so it's increasing the camber of the lifting surface. And on the left wing, it goes up. Okay, so what we're trying to do when we roll an aircraft is create a differential of lift on our wings. We try and create more lift out near one wingtip and less lift out near another wingtip, and that rolls the aircraft over. And that the differential is created by the deflection of a control surface. So we'll take our wing with our lift acting now, and we won't worry about the moment because the moment doesn't change. We're only looking at changes here, so we'll ignore the moment. And the pilot goes to deflect his control surface. And that creates a little increment of lift, and I've used the subscripts W and A here to represent lift for wing and lift for aileron. Now, I've drawn the vector there at the control surface. It's not exactly there. All it does is it changes the net pressure distribution on the wing, but that pressure distribution shifts backwards. Because of we've just put a kink in the camber of the wing, the pressure generated, the net pressure generated moves backwards. So what that has a tendency to do is create an increment of forward twist on the wing. So we create a little lift increment at the back. That creates an increment of forward twist on our main wing section. That increment of forward twist, because it decreases the angle of attack of the main wing section, can have the effect of reducing the lift from the main lifting plane. Now, if we consider the two cases here where this is before we've deflected the control surface and this is after we've deflected the control surface, if this change in lift is big enough, then we can end up with a situation where the net lift produced by the wing after we deflect the control surface is actually less than the lift before we deflected the control surface. And the opposite would happen on the other wing. So when the pilot goes to roll the aircraft to the left, the aircraft would actually roll to the right. So because the increments of lift would have been switched around. So this is what we refer to as control reversal. And as with divergence, it's related to the speed of the aircraft. So it's a problem that happens at high speeds rather than low speeds. And because these lift vectors all get bigger as we travel faster. So let's have a look at how we can calculate the speed at which this phenomena is going to occur. Okay. One other thing before we do the calculation, which I forgot to mention, is twin sets of ailerons. So airliners that have these long, slender, narrow wings tend to have two sets of control surfaces. Now, what that does is that the outer control surfaces, when the aircraft is cruising, have got no authority, because when you go to roll the aircraft, they actually generally would reverse. They would do the opposite thing that they were supposed to, because the wing is more flexible out near the tip than it is at the root. So, but at low speed, you need the ailerons out near the tips because you need the authority. At low speed, the increment of lift is small because our velocity is small. So you need outboard ailerons. So they will have two sets. They'll have an outboard set and an inboard set. And at low speeds, they're both operating. But at high speeds, they lock out the outboard set. So only the inboard set work. And that removes the issue of control reversal. But it does mean that your wing is a lot more complex and your control system is a lot more complex. So it's a fairly costly thing to implement, but it's necessary. So this is the problem that we'll consider. It's very much like the last one. The only change we've made is that now when we deflect our control surface, we've got a new angle to describe the deflection of the control surface. And this symbol here is depending on how it's written, is either an xi or a zeta. And it's a pain when you'll see when I start doing these differentials. I'm not going to keep saying it, so I'm just going to call it epsilon because dxi, m or whatever I have to say is very complicated, so I'll just call it epsilon. And so what we're looking at is the velocity at which this deflection will give us 0 increment of lift. Okay, because the increment of lift is what we're looking for when we deflect our control surface. So if you do have a copy of Megson, all this stuff is in chapter 28. So for this problem, because it's quite symbol-heavy mathematics, I'm going to copy it out of the book so I don't make any mistakes. But you can follow along if you've got a copy. Otherwise, you can look at it when you get home. Okay. So what we want to find is our increment of lift as a result of deflecting our control surface. Okay, so we have our standard half rho v squared s, and what we're going to look at is the change in the CL. So the first term is that there's going to be a dCl d epsilon, or d xi, which is very hard to say. Epsilon, it's also a very hard symbol to write because it's got a bunch of inverted wiggles. So when we deflect our control surface, we get a change. This is a parameter that we can measure, the change in lift due to deflection of the control surface. So this is like a constant times the amount that we deflect the control surface. But there's also going to be a twist of the main wing. So the twist of the main wing, we give the symbol theta like before. So there'll be a dCl d alpha times the twist of the main wing. We don't know what that is yet, so our aim is to remove this term and get it in terms of the control surface deflection, or aileron deflection. Now our change in moment, we know that moment doesn't change with angle of attack, but it is going to change with control surface deflection because we've changed where the lift is acting. So there will be a change in moment, and that is the half rho v squared SC times the change in control surface deflection, or the change in moment with control surface deflection times the control surface deflection. So again, the change in lift times EC plus the change in moment minus k times the change in theta, which in this case we're just going to call theta, it's just the angle of twist. We're not going to worry about the equilibrium theta, it's just the change in theta, equals 0. So this is the same moment equation we had before. Where theta in this case is twist due to control surface only. We're not worried about that theta that we had before from divergence. Okay. So if the control surface deflection equals 0, then theta equals 0. So what we're going to do is we're going to sub these into here and isolate theta, because what we're trying to find is the change in lift as a function of control surface deflection only. We don't want this wing twist. So we've got an equation here which has got twists in it, and it's also got the control surface deflection hidden in it. If we isolate theta, we can substitute it back into this equation to work out what our delta L is going to be. So let's do that substitution. Half rho v squared s EC So much like we had before, we end up with a numerator and a denominator. The denominator is this exactly the same as we saw it before. The numerator's got some new terms in it which it didn't have previously. What we're going to do, instead of, we're not interested in theta this time, so we're not worried about what's happening to the denominator here. What we're going to be interested in though is if this is only now a function of control surface deflection. So there's control surface deflection here. There's no thetas hidden in here anywhere. So we can substitute this back into our lift equation up the top and get change in lift as a function of control surface deflection only. So this is going to be a fairly long formula to write out. Oh, I'm already making mistakes. Don't worry about writing this big long intermediary out. All right, massively complicated formula, but it does simplify. Now, what we're looking for, and just to save me writing out another big equation, what we're looking for is when this bit here, when the whole thing, well, but mainly the bit in the brackets here, goes to 0. Because as velocity increases, we know at low velocities you've got full control authority, and at very high velocities you've got reverse controls. So at some point the change in lift will be 0. So you go from having normal controls, so a positive increment in lift, through having no increment in lift to having negative increment in lift. So there'll be as we say, a control effectiveness of 0. So what we're trying to find is the speed at which that happens. So we're trying to set that to 0. So the only way we can get that to 0 is if all the numerator bits in here go to 0. Now, the rearrangement of all those numerator bits, so rather than me write out the big equation for it, the equation we end up having to solve is this one. Now, you might say, well, how can that be 0? Because it looks like everything in there is positive. Doesn't look like there's a minus sign anywhere. Well, you write this bit here, the change in CL with control surface deflection. Well, that's a positive term. All this in here is a positive term. K is a positive term. DCL, the alpha is positive. But this term here is a negative term. This is the change in moment with change in control surface deflection. And our moment is clockwise, as the picture shows on the board. And as we deflect our control surface, the moment's going to pitch forward. So there's a negative change in moment with control surface deflection. So just be aware that this term here, when you see it in the equations, is negative. So now we can say the V reversal speed, VR, is given by this. Now let's dig around in this equation a little bit like we did before. So we're trying to increase our reversal speed. Okay, we don't want control reversal. So we can increase the stiffness of the wing. We can increase the increment of lift we get with a control surface deflection, but we have to remember that manipulations we do here are likely to affect this one as well. So the change in the moment with control surface deflection is kind of linked to the change in lift with control surface deflection. If we manipulate one of them too much, then if we manipulate this one too much, we'll probably increase this one as well. DCL, alpha we can't change. What the main thing we can do to change this, to reduce this change in moment with control surface deflection, is to decrease the distance between the aerodynamic center and the control surface hinge. So bring the amount of chord that the control surface has longer to increase the amount of chord for the control surface. So if we wanted to have a control surface, it's better to have a deeper control surface in chord and a shallower control surface in span rather than the other way around, because we want our controls, the further forward we can get this hinge location to a degree, this hinge location here, the further forward we can get the increment of lift from our control surface, the lower this term here will be. But we've got to be careful about other aeroelastic effects, which we'll see in a little while. We can't go silly with any of these changes because they all are interrelated. Flutter will be affected by this term as well. Okay, so what this means though is that for swept wings actually suffer from control reversal more than straight wings do. Let's have a look at why that might be the case. Remember our little diagram for divergence here. The control surface, the outboard control surface is sitting somewhere here. The lift that's generated from that has a tendency to twist the wing forward even more because it's a long way behind the elastic axis of the wing. So swept wings have a greater problem with control reversal than straight wings do. So that's why swept wing aircraft have to have two sets of ailerons. They don't have to, but if they want to fly at a reasonable speed, they do. Okay, so for designing for aeroelasticity, most failures we've looked at so far are related to strength. So when we look at yielding and ultimate material failure and fatigue, corrosion and wear, we're interested in the ultimate loads that we can apply to something. Even buckling, which isn't really material strength, but it's material instability, we're looking at the ultimate loads that we can apply to something. In this case, with aeroelasticity, we're mainly interested in the stiffness of the airframe. We're looking at the maximum velocities we can travel, and they're all proportional to this torsional stiffness. So it turns out that not only is the strength of our airframe really important, the stiffness of our airframe is also really important. but in both cases, we can increase our divergence and our reversal speed by increasing the stiffness of our wing here. In torsion, but we don't really want to increase the bending stiffness too much, because having a very, very stiff wing in bending can lead to problems with gusts. So imagine you had a very, very stiff wing. As soon as the gust hits you, the whole structure experiences that deflection. If the wing is a little bit more flexible, there's a little bit of lag in the system that if the gust hits the wings, they can deflect, and the fuselage may not see the same accelerations as the wings do. If the gust leaves quickly, having a little bit of flexibility actually mitigates some of the issues with gusts. So we don't over-design our bending stiffness. Divergence is not an issue for swept back wings, but is for swept forward wings. And the following things have been found to be beneficial. So we want a flexural axis a long way forward, which I said. We want our high flexural stiffness for swept forward wings. We want a very high flexural stiffness because that stops the twisting effect that comes with the bending. And we want a high wing taper. For control reversal, it's more serious for swept back wings. So the aircraft that we're mainly interested in, which are sort of big commercial aircraft, it's more serious when the wings are swept back. So to fix these issues, we generally have high torsional stiffness, high flexural stiffness to a point. We don't go too silly with flexural stiffness. Sweep back of flexural axis behind the aerodynamic axis. High wing taper and large aileron chord. So the deeper we can get the aileron chord, the better. And the use of balance tabs, which we'll see, is more of a flutter effect, but we'll look at that in a minute. All right, so that's really as far as we're going to go with static aeroelasticity. So now I'm going to introduce some concepts related to dynamic aeroelasticity. The primary one that we'll consider is a phenomena called flutter. And you all maybe have seen an example of flutter but not known it. Someone may have described it to you as resonance, but they were wrong. Now, I'll just do a very quick vibration recap before we go any further. And even the video that I'm going to show you of this event, they're calling it resonance, but it's not really resonance. When we do vibration analyses, we can have 1 degree of freedom oscillators or 2 degree of freedom oscillators or n degree of freedom oscillators. And we describe them by a mass of the degree of freedom, a spring stiffness, and a position. So a deflection, which we can differentiate into a velocity and an acceleration. We can also include a damping in our calculations, but there's no damping here. We can also have forced oscillation. So if we put an oscillating force on our system, we can see that sum of forces equals mx double dot. We can rearrange our equation to end up with the terms here. Mx double dot plus kx equals f, and we can have standard solutions for the problem. So I hope that you're not unfamiliar with vibration. This is not something that I am covering in this course. Sorry, my pen's... Okay, but you should all be aware from last year that systems have a natural frequency that they like to oscillate at. If you disturb them quickly and let them oscillate by themselves, they'll oscillate at one of their natural frequencies. If you drive with a particular oscillating force, they'll oscillate at the frequency of that force, but the amplitude of the oscillation can get very big if you're forcing them around their resonant frequency, around their natural frequency. So in here, this term in here will go to 0 when the driving force is the same frequency as the natural frequency of the system. And hence the amplitude of vibration will get very, very big. Okay. So flutter is an oscillatory dynamic instability of aircraft structures in an airflow. So we'll see, I'll show you some examples before I go through a bit of the theory. And even in one of the examples, they incorrectly talk about what flutter is. So let's just, I'll chuck up some examples. Okay, so watch this tail plane here, and it's starting to oscillate very violently. Okay, and that's very, very soon before you would end up with the tail plane falling off the aircraft. That's a special test flight in order to determine the flutter speed of the aircraft. Is this a model of a 747 fluttering in a wind tunnel? Okay, and I'll play that one again, full screen. This is just a model, and that's realistic deflections of the model too, so it's not blown up in any way. Okay. Okay, this video is called How to Break a Glider. So this is a phenomena that's also speed related. So okay, and the other one which I'll there's the bridge. Yes, there's the bridge. There it is. The bridge that you've seen a million times, but everyone would have told you this is resonance, but it's actually flutter. And even this video gets it wrong. The reason it's not resonance, resonance is when you drive a system at its natural frequency with a particular force. Flutter, there's no frequency in the wind that was driving this. The wind doesn't oscillate at 3 hertz or whatever the frequency of this bridge is. The wind is just constant. This is an aerodynamic effect. The bridge deck tilts, creates lift, which the stiffness of the bridge reacts and creates an oscillation. So there's actually lift being generated by the deck of this bridge, which is driving this oscillation. So it's nothing to do with resonance. There's no shaker there shaking it at a fixed frequency. It's an aerodynamic effect. And so that anyone who calls this resonance is misguided. Right, so this is too long. I'm not going to show you the whole thing, but Okay, so let's have a look at something that might induce flutter. And we've got two types of flutter that we'll consider, and I've called them control surface flutter and wing flutter, but they're really fairly closely related. The analysis for one of them is a one-dimensional analysis. The analysis for the other is a two-dimensional analysis. Now, let's consider, it's not the greatest of approximations, but let's just consider a slice of our wing that's only moving up and down due to bending. Okay, so there's a position of the wing which we'll call H. Now, let's put a control surface that's hinged at a particular point, and the hinge point we're assuming is here. And the CG of that control surface is aft of the hinge point. So the CG is behind, as it would be in this case. If we just put a control surface there, the CG would be somewhere behind the hinge location. Now what that means is if there's a disturbance to our wing in the upwards direction, our control surface is going to go down because its CG is behind the hinge location. So if the wing goes up relative to the wing, the control surface is going to lag. So the control surface will be behind the wing location. Then the wing's stiffness, the bending stiffness, will eventually slow the motion of the wing down and catch it and bring it back down again. But as it's accelerating downwards, the control surface is going to flip back upwards. And so the wing itself is going through a sine wave oscillation, but the control surface is lagging the bending oscillation of the wing. Now let's have a look at what's happening here. When the wing's moving upwards, so the velocity is maximum at this point in the positive direction, the velocity is maximum in the negative direction. As the wing's moving upwards, it's actually getting pushed upwards. When the wing's moving downwards, it's getting pushed downwards by the control surface. So there's a delta lift in each case. It's like when you push a kid on a swing, if you're always pushing in the direction they're moving, the swing's going to get bigger and bigger and bigger. So in this case, the wing is always being nudged in the direction that it's travelling, so the magnitude of the oscillation just gets bigger and bigger and bigger and bigger until eventually the wing breaks off. So by far the simplest way of fixing this, and it's what is done on every aircraft out there, is putting balance tabs on your control surfaces. So your ailerons have a big hunk of mass that they put forward of the hinge location to bring the CG back to where the hinge is. Because if the CG of the control surface is at the hinge, then you don't get that lagging effect. So almost all control surfaces will have some form of additional mass added forward of the hinge point, and it's a cost that we just have to bear in the design. We don't really have an option. It's not providing any structural efficiency or any ability to carry any extra payload. It's just a parasitic weight that we have to avoid flutter induced by our control surfaces. Now let's do a 1D calculation of that and work out what might happen to our system. So again, I'm going to simplify our representation of the wing. In this case, I'm just going to have an airfoil here. We're going to assume that the lift increment is in some way proportional to the velocity, because as I said, when the wing is travelling upwards, there's a nudge upwards, and when the wing is traveling downwards, there's a nudge downwards. So we'll assume that there's a proportionality there. And I'll give that proportional constant C, which we'll see in a minute, is because it behaves a little bit like a damping constant. So we'll replace our airfoil like this with this system. There's a mass, there's a positive force which is proportional to the velocity, and there's a negative force, a restoring force, which is proportional to the position. Because if h moves upwards, the wing's going to be trying to pull it back down, and if h moves downwards, the wing's going to try and pull it back up. So for a positive increment of displacement, we'll have this set of forces. Sum of forces equals ma. Okay, we're all familiar with this. So on the left-hand side of the equation, we get C h dot minus kh equals mh double dot, where the dots represent time derivatives. So I can say h double dot equals d2h dt squared, h dot is dh dt. If we rearrange mh double dot minus ch dot plus kh equals 0. So this is a typical form for a vibration solution. Now, the form of a solution to this equation, so if you've done solving differential equations before, the form of solution that fits that differential equation is this. H equals a constant for the amplitude times a constant times time times sine of a constant times time again. So these three here are unknown constants. So if we're going to try and solve what those constants are, we need some boundary conditions. But first things first, we have to differentiate this so that we can substitute it into the above equations. So h dot, and this is going to get a little bit big. So we can do a product rule here. Hang on. Just make sure my notes are the same. Just so that my notes line up, I'm just going to change that to a cos. It doesn't make any difference to the rest of the equation. We differentiate the second part of the product. We differentiate cos qt and multiply it by the first part. We differentiate the first part, e to the bt, and multiply it by the second part. So that's just the product rule. And the product rule applied again, and we're going to get a little bit clunky here. Minus h naught e to the bt q squared cos qt minus h naught qb e to the bt sine qt plus h naught b squared e to the bt cos qt minus h naught bq e to the bt sine qt. Okay, so have we got this right? So the first part is the product rule applied to this. This term is the product rule applied again to that term. And then the second two terms are the product rule applied to this term here. But we can clump some of these together. If we look here, we've got a qb e to the bt sine qt, and again we have a qb e to the bt sine qt. So there's a bit of a rearrangement that can be done. Minus h naught I'm going to take the cos out the front. Sorry, just let me decide how to write this out. E to the bt All right, so I've just rearranged it a little bit.
Isn't it q squared minus b?
Sorry, yeah, it should be minus q squared. Oh, so q squared minus b squared, yes. And this bit should be a plus there. Okay, so this is going to obviously get extremely long here. What we've got to do is substitute h dot and h double dot into the equation of motion of the system. Now, I don't know how much board space I've got, but this is going to get pretty big, but bear with me. We will get a resolution of this in a minute. And I've just gone back to the old notation, but anyway. Okay, very big equation, but things are going to get simple in a minute. So how can this equal 0? This is our equation of motion of the system. There are multiple ways that we can get 0 out the end here. Every single term here has an h naught in it and an e to the bt in it. Okay? We could say h naught equals 0, but then we've got no deflection. If h naught equals 0, then there's nothing going on here. So that's the trivial case. So ignoring the trivial case, we can go along and cancel out all of our h naughts. Now, every term also has an e to the bt in it. And e to the bt can never be 0, so we can quite happily divide through Now, we've got some terms with causes in them and some terms with sines in them. Now, if this is going to be 0 always, then it has to be 0 for any given value of time. So the only way that can happen is if all the coefficients of the cos terms go to 0 and all the coefficients of the sine terms go to 0. We don't have, because cos and sine have a different response in time, they both have, the coefficients both have to be 0. So the coefficients of the cos, we get minus m qb minus m qb, so there's two of them, plus cq equals 0. So this is our cosine. And this is our sine. So when we rearrange here, we're trying to solve for q and b, which are our unknown constants. If we rearrange, we end up with b equals c over 2m and q equals k on m minus c squared on 4m squared. Square root of. So what does this tell us? What do these constants b and q actually tell us? Well, they tell us what's going to happen to the oscillation. Okay, because our oscillation is h equals h naught e to the bt cos qt. So if b is positive, because c is positive here, what's happening to the magnitude of the oscillation? Yeah, it's increasing exponentially with time. So it's diverging very quickly. But then it's being modulated by an oscillatory bit. And what's the frequency, the angular frequency of the oscillatory bit? Q here, okay? So this is the natural frequency, and it's being changed a little bit by this damping term, but this is the frequency with which the wing will oscillate, and the amplitude is being increased exponentially. So what that looks like Okay, so there's the amplitude, which is an exponential, and then on top of that we've got a cosine. So very quickly the amplitude of the oscillation gets extremely large. And so in this case what you'll see is that you'll get flutter. If there's some aerodynamic damping, if the velocities are not very high, then the aerodynamic damping or the damping of the structure can keep this bounded. Once you get above a certain speed though, this will accelerate and you'll fall into this exponential situation. We didn't include any damping effects. So if the damping was bigger than the control surface effect, this wouldn't happen. But once we start traveling fast enough, our aerodynamic part gets bigger than our damping part. Did you notice anything about the bending and twisting of this wing? Yeah. So there's a coupling between the bending and the torsion. So the twisting oscillation and the bending oscillation are coupled together so that the wing's actually doing this. Okay. Wing flutter, which is what we'll consider now, you don't need a control surface to excite. It's a coupling of the bending and twisting modes of the wing. Okay, because generally for the wing itself, the CG lies behind the elastic axis. So if you disturb the wing, it creates a little bit of a pitch up. That creates lift upwards. The wing torsional stiffness brings the wing back around to flat, and the wing bending stiffness starts decelerating it downwards, and you end up with this sinusoidal pattern where the angle of attack is lagging the motion. So the angle of attack is in some way in phase with the velocity of the wing. So the wing here has got a positive angle of attack, which is creating more lift. The wing here has got a negative angle of attack, which is creating negative lift. So again, you end up with a divergent problem. Now we need three centers now because we have a mass as well of our 2D wing profile. We have an aerodynamic center, which we've already described. We have an elastic axis, which is the center about which things are going to twist. And we have a center of mass. And the center of mass is where, at the moment, obviously these are out of proportion. They're not this far apart, but they're normally in this order. So the aerodynamic center will be in front, the elastic axis will be next, and the center of mass will be next. And they're all a bit more compressed up to the front of the airfoil. The problem that we're going to solve, instead of a 1 degree of freedom problem now, is a 2 degree of freedom problem, because if we're going to have bending and twisting coupled together, we need an H and an alpha to represent the angle of attack, or the twist. And the H will measure to the elastic axis, and the alpha will measure as the change in angle of the section. And we'll make some simplification. So we'll assume that the whole wing chord is confusingly 2B. I've only used 2B just because that's what's in the most aeroelasticity textbooks you see. The aerodynamic center we assume is somewhere near the quarter chord. So we're assuming that there's a 0.5 times B position for the aerodynamic center. The elastic axis is some fraction of B where we've got B plus AB, so it's If A is positive, it's behind the halfway point. And again, B, 1 plus E, if E is positive, it's behind the halfway point. But A or B can be positive and negative in this case. Oh, sorry, A and E. B has to be positive. Okay, so we assume that there's a spring stiffness acting about the elastic axis, a torsional spring. We also assume that there's a bending spring, so there's a stiffness that's resisting the bending action and there's a stiffness that's reacting the twisting action. And we will do a calculation. First things first, some compatibility. We're going to have to do some switching between the elastic axis and the CG. So HCG equals H plus B alpha times this thing called X alpha. Okay, I'm just going to use X alpha because it makes some of my life a little bit easier. Where X alpha is just A minus E. Is that right? A minus E? B times, yeah. X alpha is just the distance between the CG and the elastic axis. So it's this distance here. Sorry, BX alpha is that distance. It's just a notation, make it a bit easier to write. Okay, so sum of forces in the vertical direction, so we'll just call them shear forces, vertical forces, equals mh double dot about the CG. Okay, so sum of forces equals ma is always measured at the centroid of the body. And because our coordinate system is downwards up there, h is positive in the negative direction. So h is positive when we're pointing down the board. We're going to get our lift is negative minus L minus KH H equals M H double dot CG. And I've put it in brackets because I'm about to expand it. Okay, and to make our life easier, I'm going to move the lift to the elastic axis, and instead of m0, I'm going to have now my, just because that's the notation that's in the textbook. But it's not m0 anymore. I've moved my forces and moments to the elastic axis. Some are moments about the CG, and in this case we're going to use the positive alpha direction, which is clockwise. Sorry, it doesn't equal 0. It equals I about the CG alpha double dot. Okay, sum of moments, the same way as you get sum of forces equals MA, you get sum of moments equals I alpha double dot. So these are our two equations of motion. We've got forces and moments. Okay, the only forces we've got are the lift, the restoring force from the spring, the bending spring, and the acceleration is mh double dot. With the moments, we've got the restoring force of the spring times the distance from the spring to the center of gravity, which is this bx alpha. We've got the lift times bx alpha, which is the distance to the center of gravity. We've got this my, which doesn't change. A negative restoring spring torsion from the torsional spring equals I alpha double dot. So we've got two formulae which we can start manipulating. The first thing we've got to do is get rid of the CG coordinate system. It's not very helpful to us. We want to get everything back into our elastic axis coordinate system. So we will change our h double dot CG to an h, and we'll do that by saying if h, sorry, I won't use that pen. If h CG equals h plus b alpha x alpha, h double dot CG equals h double dot plus b alpha double dot x alpha. Nothing else in here changes. So if we substitute that into the force equation and rearrange, we get mh double dot plus mbx alpha alpha double dot plus kh plus L equals 0. So this is an odd equation because it's got second derivatives of displacement and angle mixed in together, and we'll see that we'll get the same thing in the next equation, and we'll have to work out a way of solving them. Now, our ICG, what's the parallel axis theorem for mass moment of inertia? Okay, where r is the distance of the two axes from each other. So if we want I elastic axis, we can put in here bx alpha all squared. This is the distance from the CG to the elastic axis. And if we make the CG the subject, we end up with this. So we can substitute that into the equation for moments and rearrange. And I won't do the rearrangement because it's not particularly difficult. I was missing an h in my equation here as well. And if I turn them back into a standard form where all the degrees of freedom are on the left and all the forces are on the right, I get this pair of equations that we have to solve. So if we wanted to see whether these collapsed to what we expect them to, one way to check that our equations have got a sensible form is if we wanted to just look at the free vibration of the system. Let's make, just to see that, make sure that these are working, we'll say lift equals 0, moment equals 0, and the distance between the elastic axis and the CG equals 0. And see what falls out. In that case, we get m h double dot plus k h equals 0, and I it doesn't matter whether it's CG because they're at the same place now. So in that very strange case when there's no airflow and there's no lift and moment, and there's no distance between the axes, we get two independent oscillators, which is what you'd expect. You've got a spring, the wing will bounce up and down on the bending spring.
Yeah, why does lift and the moment occur at the elastic axis?
Well, lift, once we've worked out what the total net lift is, we can shift it around wherever we want. So when we shift it, we have to change the moment accordingly. So if you put the lift somewhere, there's always a couple of lift and moment. You can put the lift somewhere so that moment equals 0. If you put lift at the aerodynamic center, then the moment doesn't change with angle of attack. If you put the lift somewhere else, wherever you put the lift, you just need the equivalent moment as well. The total pressures generated by the airflow have got a combined lifting and twisting action to them. So as long as you get the sum of those two right, it doesn't matter where it's actually positioned. So we've moved, just to make the calculations easy, we've moved the lift from the aerodynamic center to the elastic axis, but we have to account for the fact that it's shifted by a certain distance. So it's not m0 anymore, it's a different moment that goes along with it. Just like if you've got a force here, you can move the force over to here as long as you give it a moment which is equal to L times the distance that you moved it. Okay, we've done the same thing. We've added another moment in there to account for it. Okay, so in that case if we move the CG and the elastic axis together so that both of the springs are acting independently, which is not a real case, but it's just checking that our equations are working, then we'll get a torsional spring where the wing will just oscillate backwards and forwards in twist, and we'll get a bending spring where it'll just bounce up and down. And those two will be independent, and they'll have their own natural frequencies. So in that case, you could never get wing flutter because there's no coupling between the two vibrations. They're both independent. You're never going to get wing flutter. To get wing flutter, you need to have some separation between the elastic axis and the CG. Because what that does is it creates this cross-coupling. See in the equations, in the equation that's based on forces, there's this cross-coupled term that's got an alpha in it. In the equation that's based on moments, there's an H double dot. So this cross-coupling is created by the space between the elastic axis and the CG. So, just to simplify our calculations a little, we're going to assume that the aerodynamic center is at 0.25 chord, which is what we assumed to begin with, so that it's at half B. So let's work out what my is then. Because this is, as I said, as we just mentioned, it was raised at a good point. This moment is the moment about the aerodynamic center plus another bit of moment, which is to do with lift. So my equals m0 about the aerodynamic center plus lift. How far have we moved the lift? We've moved it from, got B1 plus A minus 0.5 B so the lift was initially at the lift if it was acting at the aerodynamic centre. If we've shifted it to the elastic axis, we've moved it from 0.5 B to B1 plus A. So that's our moment there. Now two more assumptions, because otherwise our life's going to be a nightmare. CL naught equals 0, DCL d alpha is approximately equal to 2 pi, and we'll have a third assumption that m naught is approximately equal to 0 as well. Just the moment about the aerodynamic centre is small. We've got a camber-free airfoil. Then our equations I'm just going to put a little bit of separation in here and we'll see why in a second. It's got an H double dot there. Okay, so what we want to try and do is solve this, but we've got a situation where we've got our unknowns mixing up between the equations. So what we need to do is actually set up a set of matrix equations so we can solve this. So we're going to multiply the top equation by b, so that we get them both into moments. So the first thing we'll do is multiply everything by b. B squared, b, b. And to make our unknowns in the same units, we've got an angle here which is dimensionless, and we've got a distance here. So we'll divide by b to make it dimensionless. So now we can compare the equations, and we end up with this set of matrix equations. Now the solution to this is actually fairly complex. What we need to, when I say complex, it actually is complex. In a sense, you need imaginary numbers. You need complex numbers. So I won't go through the full solution process because I can't. It's a numerical solution process. But the substitution we make is that we make where S is complex. Okay. And if S is complex, then this term here can have an exponential part and it can have an oscillatory part. So you should know from imaginary numbers, if you put a real number into an exponent, you get exponential growth or exponential decay. If you put an imaginary number in, you get oscillation. So if you put e to the it, you'll get cos plus I sine.
Is it omega subscript h for the h equation?
No, they're both alpha. They're both in terms of the same frequency. Now, up in that equation, U equals aircraft or airspeed. We make a non-dimensional velocity just so that we can make our plots a bit easier. Okay. And what we end up with is if we solve this for S, we'll get two solutions. We'll get S1 and S2 because we've got two equations here. Okay. S1 equals S2 equals. And both of those will be a real part, which is a capital gamma, plus an oscillatory part, and I will get my little solver. And this is what the solution looks like. Okay, we've got two solutions. We take the positive parts of them, and if we plot the imaginary part, and down below we plot the real part. Now, the imaginary part, if S equals just I omega, so if gamma equals 0, we have something purely oscillatory. Okay? If S equals just gamma, so in here if we had something that was purely imaginary, this becomes an oscillation. If we have something that's purely real, we have exponential growth. So if we have a combination, so I'm going to draw the graph, so I need some board space. Oh, I better hurry up. All right, a couple more minutes and I'll have this done. Okay, so that red's not showing up very well, is it? Okay, if we end up with a situation where we get just a real answer, just an imaginary answer, we get pure oscillation. It's just a spring oscillating. If we get purely the real part, then it's exponential decay. If we get the bit in between, it's a growing oscillation. So if we get something that's got both a positive gamma and a non-zero omega, we get a growing oscillation. And what happens when we plot our... So this is like divergence. This is what we call flutter, because this flutter is growing to the point where our wing is going to break off. This is just the wing just twisting and snapping clean off. And this is just normal oscillation, safe oscillation, because the magnitude is not getting big. So when we look at our frequencies here, if we plot a non-dimensional forward velocity on the horizontal axis, so that's this v equals u on b omega alpha, the frequency of the system is entirely imaginary. Well, the real part is 0 up until a particular velocity. At a particular velocity, when the two imaginary parts meet, then the real part starts to grow. And this is what we call the flutter speed here. This is the flutter speed and this is the divergence speed. So after this velocity, the magnitude of the oscillation is starting to get bigger. Below that velocity, if we were here, the magnitude of the oscillation stays fixed. Above that velocity, the magnitude starts to grow. And the meaning of these two curves is the top curve is the torsional frequency of the system, and the bottom curve is the bending frequency of the system. So what we're trying to do is to increase our flutter speed, what we have to do is keep our torsional frequency and our bending frequency as far apart as possible. This is the, I've rubbed it off now, but this is the omega alpha and this is the omega h that I wrote up earlier. So if they start when u equals 0, if they start as far apart as possible, then our flutter speed will be big. If we bring them together, then the flutter speed will drop. So effectively what's happening, as we're getting faster, the torsional frequency is dropping and the bending frequency is rising. When they meet, you get a coupled oscillation and it just gets bigger and bigger and bigger and bigger and snaps the wing off the aircraft.